Hello, early bird. I'm sorry I can't be here today, but I want to make sure that you're ready to do worksheet 1. Hopefully you finish worksheet 1 today, but if you don't, then worksheet 1 is whatever you don't finish is your homework. So first of all, make sure you sent me a selfie with your table because I like to see you all smiling together if I can't be there. It really makes me so happy when I get them, so please do that. All right, and then the other reminder is that if you have not sent me your spring break photo, you can do that because we're going to look at them on Monday. All right, so some more background information to just kind of help make sure that we really know what simple harmonic motion is. The most important thing about simple harmonic motion is that it's an object undergoing a repeated action, so it's happening over and over and over again, like an oscillation. So like the mass on our spring yesterday was happening over and over and over again. Another example is a pendulum. So a mass on a pendulum is an object in simple harmonic motion. The most important thing is that linear restoring force, which we're going to talk about a little bit more and add some notes to that today. You know what a period is. It's the time it takes to complete one cycle. Frequency we did not talk about yesterday, but frequency is just the inverse of the period. So instead of saying the time for one cycle, it's the cycles in 1 second of time. So it's literally just mathematically the inverse. If you know the frequency, you know the period. If you know the period, you know the frequency because it's just the inverse. This equation, the frequency is equal to 1 over period, is not on the green equation sheet, so that's something you need to know. Amplitude, we already know, that max distance from equilibrium, which is not necessarily the natural length. All right, so on page 2, sorry, not page 3, page 2, we're going to add some notes. So if we have a mass on a spring, horizontal, the natural length actually is equilibrium. So that middle picture is equilibrium. Sometimes it is, sometimes it's not, where natural length and equilibrium are the same. Equilibrium is when the mass is at rest. Like you put the mass on the spring and it comes to rest. So our lab yesterday, the natural length and the equilibrium length were not the same in our lab yesterday. When the spring is compressed, the force points back towards equilibrium because that is a definition of a linear restoring force. So it's going to point to the, in this case, in the right because equilibrium is to the right. When the mass is stretched, the linear restoring force points to the left because the equilibrium is to the left. And remember, a linear restoring force is always proportional to the stretch from equilibrium or distance from equilibrium. But for a spring specifically, that makes sense, we know, because this is literally dependent on x. So the more you stretch that mass from equilibrium, the greater the spring force is. Is the linear restoring force constant then? I hope you have an answer in your head. It is not constant. The linear restoring force is not constant because the mass is always changing position. And so that linear restoring force is getting bigger, smaller, bigger, smaller. So it's going to oscillate in between those. So it's as it goes from compressed, then it's going to get smaller, then it's at equilibrium. As it goes towards stretch, it's going to get bigger. As it goes back towards equilibrium, it gets smaller, so that linear restoring force is never constant. All right, let's talk about the lab results from yesterday. So how does amplitude affect the period? If your graph looked like this, that means you did not include the origin. You have to include the origin because when you do, all of a sudden your graph looks very, very different. So if you look at this graph, all I did was I just put it, I zoomed out the graph, so I'm looking at the data in a more comprehensive way. So now that I look at this, is it quadratic? No, because a quadratic graph looks like a parabola. This is definitely not a parabola. Is it a square root? No, because there would be a lot more variance in my data. Like, there would be a square root shape like this. It's not a square root. Is it an inverse? No, because as amplitude gets bigger, period does not get smaller. Is it linear? Linear would mean like either as amplitude gets bigger, period gets bigger, or as amplitude gets bigger, period gets smaller, but like that change is constant for every equal increase of amplitude. And that's not happening either. And actually what we say is that as amplitude gets bigger, there's really no change in period at all. And so what that means is that there is no relationship. It is just a horizontal line. How does mass affect period? So if we look at this graph, you can see at the very end there's some flattening that's happening, which indicates a shape where the end becomes a little bit more flat, which is a square root. So how do we square root? We need to square the y. So if we want to linearize a square root graph, we need to square the y-axis. So we're going to square our period and graph versus mass. And if we do that, we do get a line. So to write a physics equation for that, on our y-axis is t squared, on our x-axis is mass, m. So this is m, it's not the slope m. I'm leaving a blank for slope. Then I need to put units on my slope and my y-intercept. My y-intercept is 0. So for b, I'm plugging in 0. Seconds squared, it's not seconds because my period is squared. So I'm graphing t squared, so the units are seconds squared. And then for my slope, it's going to be seconds squared over kilograms. And then whatever that number is. And we tell you, actually, what the slope theoretically should be. So what should this actually be? And it should be 4 pi squared over k. So in number 5, I think it was, we gave you the theoretical value of the slope. And again, this is just like plugging in that theoretical value of our slope. But on the equation sheet, maybe some of you saw this, on the equation sheet, it's not written like this. On the equation sheet, it looks like this, which is just taking the square root of both sides of this equation. So we get t is equal to square root of 4 pi squared is 2 pi, and then square root of m over k. So you just square root both sides to get this equation. It's the same equation. You can use either one, but this is what's on your equation sheet, the one boxed in red. Okay, so number 8 is really just proportional reasoning. And so if we double the amplitude, there's not going to be any effect on the period. If we double the mass, we are going to affect the period by square root of 2 because t is proportional to the square root of m. If we make the spring constant double, a bigger spring constant is going to mean a smaller period, and specifically it's going to be 1 over square root of 2 times t. If we change the mass and change k, and again, this is kind of just, we're doing proportional reasoning, you should get square root of 4 over 3, because 4 over 3, and then this is a constant. Okay, so just to recap, experiment 1, amplitude does not affect the period of the spring. Experiment number 2, the hanging mass is proportional to the square of the period. And so this is the equation that is on the equation sheet that describes both of those relationships. All right, let's talk a little bit about energy graphs because we have not done these, and these are going to be on worksheet 1. So why are there no lower quadrants for this graph? Why did I graph it where none of the energy, the y-axis, is negative? Because energy can't be negative. All right, if we're going to graph mechanical energy of the spring mass system, There's no forces acting on the spring mass system. And so there's not going to be any work done. So it'll look like a horizontal line, no matter where the position is. Now, why do I have negative positions? The negative positions represent compression of the spring. So if this is equilibrium, these are stretching the spring, and then the negative positions are compressing the spring. So when the spring is fully compressed, how much of the energy is spring potential? When the spring is fully compressed, it's at rest, so there's no kinetic, so all of the energy is spring potential. When the spring is at equilibrium, how much energy is spring potential? None of it. So none of the energy, so there's zero spring potential energy at equilibrium. How much energy at full stretch is spring potential energy? It's the full pie, so it's going to be all of those pie charts. So our spring potential energy looks like this. And then you can say, well, I know what kinetic energy is going to look like because energy has to be conserved. But we can also think about it based on what we observed with our mass. So when we fully compress the spring, the mass stops for a split second. So that means there's not going to be any kinetic energy at full compression. At equilibrium, the mass is moving really fast. So all of the energy is going to be kinetic. And then at full stretch, the mass has to stop because it's turning around. So it stops for a split second, so there's not going to be any kinetic energy. All right. So next, you are ready to work on worksheet 1 with your group. Whatever you don't finish is homework. On Tuesday, we have a lab assessment on springs. I will see you all on Monday, and please be diligent in your work, as I know you will be. And I hope you have a good weekend, and I hope you have no homework. All right.